Okay, in this video, I'm going to show you how you figure out the value for the Gaussian integral, which is a very useful integral in math. So it's basically you write it as capital I is equal to the integral from negative infinity to infinity of e to the negative x squared. Now, um, there's no way I have no way to integrate this right now, so we're going to actually use a trick where we say I squared. So if we say I squared equal to, it's going to be this multiplied by itself. So we'll say integral from negative infinity to infinity of e to the negative x squared dx multiplied by itself. But what I'm going to do in this one is I'm going to change the x to a y. It's the same thing. It's just a variable for this definite integral. But I'll show you why. Negative infinity to infinity of e to the negative y squared dy. Okay. These two we can actually put, since x is a constant with respect to y, we can put this inside that e to the y integral. So I'm going to do that. So I'm going to say integral from negative infinity again from negative infinity to negative infinity of e to the negative x squared dx times e to the negative y squared dy. And since these are all constant with respect to each other, we can actually multiply the e's to the negative whatever terms together. So I'm going to do that from negative infinity to infinity of e. Oh, sorry. We get another integral. Negative infinity of e to the negative x squared times e to the negative y squared. Hope you can see that. Dx dy. When you multiply two bases with different exponents, you add the exponents. I'm going to do that. Equal to integral negative infinity to positive infinity. Again, e to the negative x squared plus y squared. Minus y squared, sorry. X squared minus y squared dx dy. So this is a double integral over 2D space now. So again, I still have no way of integrating this, but if we turn it into polar coordinates, we can do that in terms of r and theta. So that's what we're going to do. So first off, the bounds for r and theta, the bounds for x and y are infinite. So it's basically covering all of the space. So if you can imagine, what we can do is we can have theta going from 0 to 2 pi. So if this is the origin and this is the ray going up, we can basically go around 0 to 2 pi. It should go this way for you guys. So it's going to go like this. Oh, no, it is this way for you guys. So it's going to go like this. And the r is going to go from 0 to infinity. So I'm going to write that in bounds out. So from theta is equal to 0 to 2 pi, and r is from 0 to infinity. E to the negative x squared minus y squared is equal to negative times x squared plus y squared. You know, well, x squared plus y squared is equal to r squared. So it's going to be e to the negative r squared. E to the negative r squared. And in polar, you have to multiply the integrand by r. I might do a video on that. It has to do with the Jacobian, but it's going to be r d theta. Okay, I'm going to do two things in this step. I'm going to evaluate this d theta integral because there's no actual theta terms in there. It's just going to be 2 pi because it's from 0 to 2 pi with a constant. And I'm also going to add a limit. And so I'm going to replace this infinity with a b. I'm going to do limit as b goes to infinity. So it's not a improper integral anymore. Equal to 2 pi times the limit. B approaches infinity. Integral from r is 0 to b e to the negative r squared times r dr. Okay, next thing I'm going to do a substitution where u is equal to negative r squared. Du dr, if we take the first derivative with respect to r, is going to be equal to negative 2r. So if we split that up, that's going to be du equal to negative 2r dr. So that's dr is equal to du divided by negative 2 r. Okay, so that's what we're going to do. We're going to replace this dr with the du over negative 2r. So that means that a few things. That means that this r is going to get divided away, which is why we wanted to turn into polar coordinates. It's divided by 2, so we're going to get rid of this 2 up front, and it's multiplied by negative 1. So I'm going to actually flip the balance. So b is at the bottom and 0 is at the top. And also I'm going to plug in the u is equal to negative r squared for the balance. So 0 will become 0 squared is 0, and negative b squared is negative b squared. So I'm going to do that. It's a few things right now. So it's going to be pi times the limit as b approaches infinity from negative b squared, it used to be on top, now it's on bottom, to 0. I'm going to put the u in there, so e to the u du. Okay, now this is a lot easier to integrate. It's just this e to u is just e to u. So it's equal to pi times the limit as b approaches infinity of e to u from negative b squared to 0. It's equal to pi. Let's just evaluate that. Limit b approaches infinity of e to the 0 is just 1 minus e to the negative b. Let me write that better. Minus e to negative b squared. Okay, let's evaluate this limit. As b approaches infinity for e to the negative b squared, negative b squared is going to approach negative infinity, and as e to the x approaches negative infinity, it approaches 0. So that term basically becomes 0. So it's just going to be pi times 1, which is equal to pi. We're not done yet though, because we integrated for I squared. So it's equal to I squared. So I is equal to square root of pi. Let's write that up here for our answer. Square root of pi. One thing I actually haven't done yet is shown you what this integral, this curve for e to the x squared looks like. It kind of looks like a normal curve actually. If you can see that. So basically we integrated the entire thing from the area under this from negative infinity to infinity, which is just square root of pi. I'll show you a few examples of why this integral is important. First, with the error function. Basically, the error function is it's like this integral, but instead of being bounded from negative infinity to infinity, it's just from negative x to x, where x is the input of the error function, and it's also divided by 1 over the square root of pi. So the curve is normalized. So I'll write that down. You write ERF of x is equal to 1 over square root of pi times that integral, but from negative x to x of e. I'll use t for the variable, e negative t squared dt. So if you can imagine, we couldn't actually integrate this. You have to use like an approximation from a numerical method. However you're going to do that. If you are going to do that, because this function e to the negative x squared is even, you might want to do 2 over square root of pi integral from 0 to x e to the negative t squared dt, just because you're going to repeat a lot of information when you're approximating it on that interval. And this function actually looks a lot like a tangent curve or a logistic curve. It's kind of like it has two horizontal asymptotes at -1 and 1, and it just kind of looks like this. And that's very similar. And yeah, so that's why we divided it by square root of pi. So the limit as it approaches infinity is just 1, and as it approaches negative infinity is -1. Another example of where this is used is in the normal curve. I might do a video on this, but if you want to derive the normal curve, it's y equal to, let me just get this right here. It's in terms of rho and mu, which are the standard deviation and mean. Rho square root 2 pi, so you can imagine that square root of pi from there. That's where that comes from. Times e to the negative x minus mu squared over 2 rho squared. And this is the normal curve where rho is the standard deviation and mu is the mean. And that's it. I think that's pretty cool interval. It has a lot of uses.